We are not. What's up?
Yeah, Ferguson.
Yes. We have many. This is my time. I don't think this is level.
Is there a little bubble on the top?
We should.
Do we need to plug into the big TV?
Yeah, we should actually check that that works.
I agree.
We'll just linger outside until it's Kelsey, mostly my speakers.
So here's the thing with this computer.
Yes.
On my Mac,
Yes.
I have a thing that says turn the screen into.
Yeah.
Sam, if this is an issue, we can also use my computer, which is a Mac.
It says that.
Oh, okay, hey.
There you go. Was it up there? Is it actually up there?
It did a thing. It says that I'm connected to a screen.
That's via the HDMI, right?
Yeah.
Okay, hold on.
And then we never got the audio thing. Oh, yeah. Is that you?
Yep.
Nice. And then just the audio.
No,
change of plans.
It's back there in that corner. But again, that table's going to get blasted.
Yes, the speaker has to stand there. Great.
Is that okay?
Yes.
I'll turn the light off and then they can just stand in front of the room.
Okay. Do you have to see your slides on the computer? No, like, do you have to do the top?
I can turn around and look back at them.
That's what I was hoping you would say.
How's life going?
Welcome. Good. Yeah.
I unplug you for a second so I can plug the speaker in.
That's fine. That's fine.
Yeah. Yeah. Yeah.
Okay, you should have power in.
We're good.
Yeah. We do trivia first. A little bit of trivia. Kelsey will give her talk. And then I'll come back, give trivia answers, announce winners, and then we'll switch back over. Would you rather do this talk from your computer or I pull up the slides from this?
Yeah, whatever is easier. If it's on your computer, then let's just not mess with it.
I took out the COVID.
Right before you give your talk,
I took everything out already.
Sorry?
I took the stuff out
you'll
already.
have to focus on microphones or just
Even better. Great.
flip on my front.
Let's move
nice.
these
Okay.
back, and you can sit back there.
Oh yeah.
Also, I was delighted to find out.
Great. Open chair. This is your laptop.
Oh, we also have that you can use. Or you can use your own.
Yours might be better.
It might be.
Yeah. Oh, and I forgot the laser pointers don't work on TVs.
Yeah.
Because this is so sorry about that.
Okay, so just to clarify, you're doing trivia on this laptop.
Yeah.
Trivia is that we're then going to switch the HDMI to this laptop. Okay.
And back to that for
If it's easier, I can just take a video.
it's totally. Do we want to make sure that your slides are live?
It's a PDF. So
It is not hard. We'll just pull down the HDMI and then plug it into your computer.
Sam?
Yes.
No, we can't.
Can you go back and stand there?
I'm just double vibe checking. Well, that's my face. how long do you typically have people talk?
About 30 minutes ish.
Gotcha. Okay.
Plus about 10 for questions, but it's like it's super chill time.
Yeah.
So if you're over or under that's fine. Yeah. I'm doing like a janky Zoom.
No, I know, it's fine.
Oh, we need to.
Well, that's not what you want to see.
I should have checked that first.
Okay. That's fine.
This is fine.
That's
It
fine.
just wiggles a little bit.
Yeah.
So you were going to sit here a little bit back to like kind of
Yeah. Well, that's problematic. Maybe it doesn't like being sent to USB A and then back to USB C.
Maybe it'll be different when we put this laptop.
No, I don't think so.
Could it hurt to try?
Because Alex's slides are.
On here?
Yeah.
Cool.
I guess I should have thought to check that sooner.
Yeah.
Time to Google it.
We also have 3 minutes.
Yeah, I saw that.
If we have to start and do trivia and figure this out while trivia's running, let's go.
Yeah. It was all going so well.
Okay.
And unlike every other scenario, the speaker camera doesn't do
I know.
a lot of people here. It's cool, right?
Yeah, it's very possible. I don't know if the space is big enough. We'll see.
Definitely not. So keep your talk. I think that we should just try and start rolling.
Yeah.
If you want to try and do this, I can start doing trivia. Or I can try and take over this.
I think I need to just do trivia,
Okay.
and then I guess you can troubleshoot that.
Yeah.
And if that's we just go straight ahead.
No, we'll just stream that and take our two slides. Yeah.
You could also swing the camera around manually, like point at the person for a little bit, and then when you guys are
We can. Yes.
We also could just point this at the slide.
Also, this isn't attached to anything.
Well, yeah.
It's just hold there.
You can,
Okay, we got it.
But I think it's fine to, and that's a good idea. So you can just point this at the screen when the time comes.
Yeah.
Okay. Yes. I will. Oh, I guess I need to announce the trivia first. Sounds good. I need to announce that.
Yeah, no. You should move.
Hello, everyone. Is this audible in the back of the room? I don't know how to do that. While they figure that out, I just want to thank you all so much for coming to Astronomy on Tap. And we always start with a fun little round of trivia. So if you'd like to participate in trivia, you would come up and grab a sheet and pencil from our lovely trivia helper, Barbara. And if you are a professional astronomer, you're welcome to participate, but you will not be counted in. You will get to win, but you'll get to play. Please let us know that on a sheet, and otherwise help me grab a sheet, and we'll start in like maybe 5-ish minutes.
Testing.
D, black hole jets.
Questions,
Is
right?
to measure A,
Cool.
the positions of galaxies, B, the positions and motion temperatures of planets, or D, sizes of black holes. Question 8. The motion of satellite galaxies around the Milky Way is especially useful for studying dark matter because A, they're mostly made of gas, B, their stars are very hot, C, dark matter dominates their gravity, or D, they orbit inside the sun. Question 9. The Auriga? Alright. The simulation is called Auriga, but the thing in space is called Auriga, which is interesting.
Because the Europeans don't get it right.
It's because the Europeans don't get it right. Alright. The Auriga simulations model how A, Milky Way-like galaxies grow, B, oceans form on exoplanets, C, how stars explode, or D, how moons break apart. If you can pick among the themes of the questions, you might get a hint to the answers. And finally, Question 10. The Apostle simulations were created to study the environment of A, the Kuiper Belt, B, the early solar nebula, C, the local group consisting of the Milky Way and Andromeda, or D, the Virgo galaxy cluster.
We're going for 0.
All right. Now, I'm done reading them, but I'm going to go back to the top and give you another 10-15 seconds for questions you can finalize your answers.
No, I didn't. What are you doing? Yeah, that's my answer. John writes it. More fervent. Yeah. You would turn back to my How do you write? We just failed the exam. No, you could have inferred by like applause worthy.
Yeah.
I like your choice.
Yeah. I like a we're in a Roger.
You're a fan.
Oh yeah. It's actually accurate and it closes up.
That's great. I'd worry about your cancer risk.
Just pray how we're rated, bro. Yeah, I don't know where I was going.
All right, that has been the trivia. We will have our first speaker give her talk, and then after our first speaker, we'll announce the answers and the winners. And so, if you have your trivia sheet, please come up and hand it to our lovely trivia assistant, Barbara. And in the meantime, we'll work on getting that first presentation up and ready for you. See you soon.
And bring your golf pencils.
And make sure to bring the pencils back. We'll be really sad if you leave them.
You'll go.
did I touch it? Okay. I'm gonna introduce you. Oh, sorry. And this is still a conversation. And anything
Go.
Should I go?
You're not mine.
Should I mic?
No, go.
No, we have two.
This is hot enough. It's fine. I say on a hot.
Oh my god.
He looked really excited.
Thank you all again so much for coming out to Astronomy on Tap. It is my great pleasure to introduce Dr. Kelsey Lund. She is currently a postdoc at the University of Washington at the Institute of Nuclear Theory, which sounds really cool and doesn't always do astronomy stuff. So really happy to have her here. She got her PhD jointly between North Carolina State University and the Los Alamos National Lab. So going back and forth between the two coasts of the country. And yeah, she's going to talk about dead and dying stars. It'll be fun.
I have to do both.
Yes.
Do I have to stand over here?
Yes.
That's fine. Unexpected. Okay, sorry. I was not clear on how that was going to work out. Thank you so much for the introduction and to all of you for being here. Can you hear me okay in the back? Oh, cool. All right. So I'm super happy to see you all here today. I am going to talk, now that we all have our beers, I'm going to talk to you about wine. Specifically, I'm going to talk to you about fine French wine. All right, so the holidays are coming up, and this can be a time of some stress for some people as they think about what should I get for my loved ones? What should I get for my partner? What should I get for my family? What should I get for myself as just a little treat for how well I've done this past year? Well, if you have some money to spare, what you could do is you could go down to your local fine wine dealer and drop about $80,000 to $110,000 on a nice single 750 milliliter bottle of wine. If you feel like it, They also have them at the grocery store, but we're better. We're nice, we're fancy. All right. Cool. You could do that. This is a thing that people do. They'll drop the cost of a house on a bottle of wine. You want to make sure that what you're paying for is actually what you're getting, right? So then the question becomes, well, I don't know if this dealer is actually really good or not, or can I trust them? How can you guarantee that this Chateau Lafite Rothschild 1868 is indeed what it says it is? They've told me that the best wine in the world comes from the Bordeaux region of France, and I think that that's where this one is from. How can I know that this is actually from the Bordeaux region of France? Well, they'll tell you that France has come up with a very clever way of promising you that what you're buying is actually what you're getting. I don't pronounce French, but the appellation d'origine, okay, that, anyway. It's controlled, okay, it's controlled. Basically what it is that they will tell you that if you look really closely at the labels, actually, sorry, the laser pointer doesn't work, but if you look at where I highlighted in red, if you look very closely at the labels, what you'll be able to see is basically I don't know, to me it seems like a pinky promise that, yep, this comes from that region of France. They have, various different designations for the different regions of France. One you might notice is the Champagne one, up there in the northeast kind of corner of France, Bordeaux down in the south west. All right, and there are a ton of rules that go into this, like the font can be, I don't know, I'm not an expert in French wine, actually, I lied to you. But basically, this is what you can do, is you can look at the label and say, yep, that's the appellation, and that's how you know that that wine is French. You say, wait a second, it's a label. Like, we've been making things on paper for hundreds, thousands of years. If they have the resources and time to make a label, well, maybe so do I. And this was actually something that happened. This was a big scandal in the wine world a couple years ago. This article from NPR is from 2013. And these are all photos of evidence. You might recognize in the bottom, I guess your right corner, some of these bottles. That one that I showed right there is actually a photo from evidence. Basically, this guy basically took kind of lesser quality wines and passed them off as these super fancy bottles of wine with these, appellations, and then charged thousands of dollars for them. The reason this guy got caught actually was because he was selling more bottles of wine than were actually produced. And the guy, or the person from the cellar, was like, hey, math isn't mathing. So something's going on here. Went to prison. In doing the research for this, I found out he just got out of prison. So watch out, I guess. I don't mean to slander anybody. I'm not about that. But yeah, so that's a thing. All right. So how can you really know? Well, strontium comes to the rescue in this sense, obviously. Strontium, as some of you might have recalled from the periodic table, I've taken a little snippet of the periodic table. So you can see that vertically, so it's in the second column there between calcium and barium. If you look horizontally, it's between rubidium and yttrium. So it has 38 protons. So if you're into geology and you like rocks, you might recognize the name that celestine, I believe. Is a mineral that has strontium in it. If you've seen red fireworks in your life, chances are you've seen strontium lit on fire, which is what gives the red to some of those beautiful fireworks. And I've never played this, just as a disclaimer, but apparently in Fallout, the video games, strontium also makes an appearance because strontium-90 behaves very much like calcium, and it's a product of nuclear fallout that gets absorbed by our bodies in much the same way as calcium. So particularly dangerous, but its stable isotopes are fine. Speaking of isotopes, the periodic table is a wonderful way to write down all the different elements that exist in nature. They're nice if you're a chemist. There's information that's missing if you're a nuclear physicist. And so let me introduce you to the chart of the nuclides, which is kind of an extra-dimensional periodic table. So there's a quote that I found from apparently Bill Bryson, which was talking about how electrons give an atom its personality. So if you take electrons away or if you add them, fun chemical things happen. I think about nuclear physics, so I think that a proton gives a nucleus its identity. That's going to characterize what chemical it is. How many neutrons it has is going to give it its personality. So this is where you get radioactivity. If you add too many neutrons or if you take too many neutrons away, it's going to become radioactive and do some fun things. Okay, so basically what we do is you can see on the vertical axis on this little figure that I have on the right, the different elements. So we organize this by atomic number, so increasing in Z, number of protons. And as we go to the right, we have increasing neutron number. So it's basically all of the possible isotopes of every element that we've ever measured. And this is just something that we look at, when we want to look something up, like how stable something is. And so you can see right in the middle there is strontium. It has 4 stable isotopes. These in particular are colored by their half-life, so basically how stable they are or unstable they are, lighter being less stable. Okay. How do we use this? Well, someone has figured out that if you measure the amount of strontium-87 to strontium-86, so these are 2 different isotopes of strontium, they're not the same. So if you measure the soil in one region of France, in particular, I took this from a paper from 2018, where they measured basically soil samples and found out how much this ratio of strontium was in different regions of France, and they mapped it out. And they drew lines from Bordeaux actually to Paris, Luxembourg, and somewhere else in the south of France that I don't remember, I'm sorry. And they have basically colored it by these different ratios. So one thing that you could do, presumably, is say, well, let me measure how much of these different isotopes of strontium there are in this bottle of wine. And if it doesn't match that region in Bordeaux, that's bad. I should not buy this bottle of wine. So
Great, nuclear physics is a super useful tool for dating wine. Hooray! Okay, thank you, bye. Okay, but hold on, this isn't astronomy. Wait, what? Hold on. I promise there is a point. What about the stars? To answer this question, but what about the stars? We have to think about, why are there different isotopes in the first place? Why can we do this study of measuring the ratio of strontium-87 to strontium-86? This is the field of nuclear astrophysics. So this is what I do. I spend my time basically thinking about this plot, and what this plot is showing is how much of the different stuff there is in the sun, in the solar system. By stuff, it's organized here by Z. So again, this is like your periodic table in increasing atomic number. So you have all of the different elements on a logarithmic scale, right? So way at the bottom here, at the very left, is hydrogen. Most of the universe is hydrogen. But there's a lot of stuff that's not hydrogen, or else we wouldn't be here tonight having our very nice beers, right? So that's what I do, is I think about, where does all of this stuff come from? Basically, what are all of the different microphysical processes, so this is where the nuclear part comes in, affect how this stuff is made. One tool that I use to do this is nucleosynthesis. So that's what I'm going to talk about. Actually, what I'm going to talk about is nucleosynthesis, which is the process of making new nuclei from existing nuclei, so things like atoms that already exist, nuclei that already exist, and the things that make up nuclei. So if you have protons, if you have neutrons, how can you combine them in different ways, in different scenarios, to make different elements, like in the sun? Okay, so I'm going to start. Again, this is not my area of expertise, so there you get one slide about this. Big Bang nucleosynthesis. In the very beginning, there was Big Bang nucleosynthesis, and this is basically where all of the hydrogen and helium, not all of it, a lot of it, was formed, basically from protons and neutrons. Okay, so you have a nice little diagram here that just shows you that when you throw a proton and a neutron together, you get something called deuterium, which is an isotope of hydrogen. And then if you keep doing that in different ways, you end up with helium-4. So this is 2 neutrons, 2 protons. Okay, so in the Big Bang, in just the first few minutes of the universe, you've made most of what is in the universe, the hydrogen and the helium. Okay. You can make a tiny amount of lithium, but don't worry about that. But basically, this idea was proposed in the 1940s that you could build up heavier nuclei by just adding protons and neutrons to them, right? So it's kind of like Legos, right? If you just throw more neutrons, more protons onto a nucleus, you get new elements. Great, it's a good idea, and it works if you're talking about hydrogen and helium. But there's more stuff in the universe than hydrogen and helium, as I've hopefully at this point made clear. So we've only really gotten a tiny amount of that plot that I showed you before. Where's all the rest of everything? Where are we? We're not here yet. We were not made in the Big Bang. Sorry. All right, so I know we already did the trivia, but I do have one question for you. If anybody feels like answering, please go ahead. What's the difference between a planet and a star? Fusion, actually, very good, yes. So a star is considered to be born once fusion ignites, right? So once it starts taking the hydrogen atoms of which it's made and turning them into helium. So this is fusion ignition, and this is what makes a star. So I do love this picture. I love these little pictures of nebulae that show stars in their nurseries. So we talk a lot about stars in very human terms. I find it very endearing. I'm a big fan. All right, so we have stars. They are going to start their lives by fusing hydrogen into helium. Now, how they evolve over their, millions of years of lifetime is going to depend on how massive they were when they were born, right? So we have stars that are about the mass of the sun. The number down here at the very bottom, 2 × 10⁻30 kilograms, that's a lot of kilograms. There are stars that are way more massive than that, right? So some are about the mass of our sun, some are 10, 20 times larger than that, okay? And so basically how massive they are determines what the dominant energy production source is going to be, right? So stars that are kind of like our sun are going to go through what's called the PP chain. This is the proton-proton chain, but we like to just shorten it to PP chain. Heavier, more massive stars have denser central regions where they're basically able to achieve the temperatures and pressures that are necessary to actually add a third helium nucleus to two existing ones and do what's called the CNO cycle, so they can use carbon, nitrogen, and oxygen as catalysts, and so they can make heavier elements. So heavier star, heavier elements. How nice. Okay, great. But like all good things, if you have something that runs on fuel, that fuel is not infinite. Eventually, it's going to run out. And so this is where we get into the stellar graveyard. This is where the part of the dead stars that I mentioned is going to play. So how do stars die? Well, how they die also depends on how massive they were when they were born. So, you know, your initial conditions say a lot and have a lot to do with how you live out your life. Basically, the larger the star is when it's born, the faster it's going to die. So the shorter lived it is. So these massive, massive, massive stars basically burn through their fuel so quickly that they just die in a couple million years. And that's short on astronomical timescales. Okay, so low mass, now we've shifted the range to about 8 times the mass of the sun. Okay, what you can do is you have this core. This core is, and again, we're talking here ash, burning. It's all very like a campfire. It's kind of nice. But basically you have this core. This core is helium, kind of inert. There's still burning happening in the outer region of the star. And what you can end up with is a situation where you have this outer shell that just expands. And this is probably what's going to happen with the sun, is that it'll poof up and become about the radius of where the Earth is. So a homework question that I remember getting in undergrad is calculate how big the sun will get, whether it will envelop the Earth or whether it will just kind of barely just touch us. So it might be fine. Anyway, the remnant is what's called a white dwarf. Okay, so this is where you get all of these beautiful pictures of planetary nebulae. So this is just gas that's been puffed out. These are colorized images. This is a very important skill for astrophysics, basically how we can take information from different wavelengths of light and translate that into something that we can interpret. Okay, so we have these beautiful structures. Notice that they're pretty spherical approximately. And this is just coming from the puffs, the nice quiet depths of stars. All right, well, what happens if you're a massive star? If you're a massive star, things get way more exciting, okay? What you get now is the ability to basically squish things more and more and more in the core. And so you end up with this kind of onion shell there. I know there's a Shrek reference in there somewhere, but basically as you get closer and closer to the core, you have higher and higher temperatures and densities, and you're able to produce heavier and heavier elements until the point where you get to iron. And you can see here in this little box, it shows the approximate time scale on which all of these different processes are happening. You see that it changes drastically, right? So you're starting with hydrogen, you're burning hydrogen for about 7 million years. That's a good amount of time. You burn through all of your silicon in a day, approximately. And this is what's called a core collapse supernova. Okay, so the reason it's called a core collapse is because basically everything collapses in on itself because there's nothing pushing out all of that material, keeping it stable. And again, depending on how massive the star is, you can either get a neutron star or a black hole. So this is where the neutron stars and black holes in our galaxy and our universe come from. This is, okay, we always have to stop for a pretty picture. I love the pretty pictures. But also, nice little cultural aside, there was a supernova that happened in the year 1054, and there are records of this supernova being visible. One notable example that I want to go see this is in Chaco Canyon in New Mexico. And it's interpreted as being a depiction of the supernova. So you can see like the hand and then the star, and then I think the little arch thing is supposed to be the supernova, I believe. So that's pretty cool. Supernova are part of our lives. We've seen them before. Hopefully, we'll see some again soon. Hope for Betelgeuse. Just cross your fingers for me, okay? All right. So great. We've made it all the way up to around iron. There's still a lot of stuff left. Now, what I'm not showing you is a plot of binding energy per nucleon for all of the different elements, because don't worry about it. Iron is one of the most stable nuclei. So what that means is that all of those processes that the stars were doing to get energy, when they were fusing hydrogen together into helium, they were deriving energy from that. They were gaining energy from that process. You can't do that with iron. You can't fuse two iron nuclei together and get energy out of that. Okay, so iron is the star killer, I think. Oh, I had that in one slide. I guess I took it out. Oh well. So how do we get past iron? If you put more and more protons in it, you can do that, but it's kind of hard. remember magnets, if you try to stick, the same pole of two magnets together, it's really hard. So that's not really a very sustainable method to make heavier elements. But there are neutrons. Neutrons don't really care about your charge. They'll just stick. All right. So in order to make all of the rest of the elements that we have on this one-dimensional periodic table, we need neutron captures. Okay, so this is basically the procedure of neutron capture. You take your you take your nucleus. Here it's a single proton. Usually it's probably going to be heavier than this. There are going to be lots of protons and lots of neutrons already, but at the most basic level, you start with a proton, add a neutron. Okay. Here's the problem. Neutrons are not stable particles. Neutrons have a lifetime of about 15 minutes. And if you remember from the little snippet of the chart of the nuclides that I showed you before, most elements or most isotopes of all elements are not stable, right? So what's going to happen is that neutron is going to want to turn back into a proton through a process called beta decay. Okay, and so that movement is going to go, if you imagine the chart of the nuclides here, is that the neutron capture is going to take you over to the right one way, and then the beta decay is going to take you up and back. Okay, so diagonally. Okay, and this is the process of beta decay. So neutron capture to build up elements, beta decay to decay back to stability. The nuclei don't want to be radioactive. That's the whole point of radioactivity. All right, so one place that this gets really interesting is if I look at the section of the chart of the nuclides, here you can see the elements. I have mercury, lead, polonium, radium or radon, don't worry about it, thorium and uranium. Thorium and uranium are the interesting ones. Particularly, you probably have heard about uranium. If you have Fiestaware from like the 50s, I think there's some in it. So just, it's fine, I wouldn't worry, but we know about uranium. We're familiar with uranium. The coloring here in this particular slide, the darkest gray are the stable elements. You'll notice that they end here at lead 208. That is the heaviest stable element, isotope of an element. But the ones that are kind of a slightly lighter shade of gray, but not the lightest shade of gray, have a half-life of more than a year. Now, a year is kind of a low cutoff. Some of these have half-lives of billions of years. So their half-life might be the lifetime of the universe. So they're basically stable as far as we're concerned. So how do you go with this basic neutron capture that takes you to lead 208? How do you capture and make these, not technically stable, but basically stable isotopes? Well, this is a problem because you have all of these super radioactive nuclei in the middle here. So how do you get around them? Well, remember, you have to go one step out, one step back. So just take a lot of steps out. And then when you go back, it will put you in the place that you want to be if you want to make, for example, uranium-238 or 235 or whatever, basically a stable isotope you want to make. So this is the R process. This is the rapid neutron capture process. We're very creative in naming our nuclear processes. It's R because it's compared to the S process, which is slow. I'm not even joking. That's actually what it's called. And we also have the I, which is the intermediate process. Not quite slow, not quite fast. All right. We have a problem. Where are there this many free neutrons, right? Neutrons don't just exist by their own for longer than about 15 minutes, so where are we going to get this? Well, remember, we've already talked about stellar remains. One of those is a neutron star, which is kind of a big ball of neutrons. And I say this, we don't know what's actually in the center of neutron stars. We don't know their composition from a nuclear physics point of view. It gets very complicated. People spend their whole life studying this. It's very interesting. I have a quote from a friend of mine. He said at a talk, neutron stars are the most interesting things in the universe. I agree. They're super complicated. They're very interesting. Anyway, imagine an object that is about the mass of the sun, slightly more massive actually, and put it into a ball that is the size of a city. Okay, so this is a figure on the right. It's a figure from the European Southern Observatory that they made comparing it to the city of Munich. On the left is a picture that I made hiking up the Valles Caldera, which is approximately the diameter of a neutron star. So this is the idea, this is the scale that you're thinking of. So these objects are incredibly dense. They're some of the most compact objects in the universe. So take a lot of mass, put it into a tiny, tiny little ball. Okay, but yeah, we have neutrons here, but how do we get them? That doesn't really help us if we want free neutrons. They're stuck in that neutron star, right? your uranium, your Pyrex dish or your Fiesta, where it doesn't have neutron stars in it, it has single nuclei. So how do we get those? All right. Well, imagine if you were to throw two wet tennis balls together, you get a lot of stuff out. And so if you have a neutron star and you smash two of them together, you can get a lot of stuff out. And this is when this happens, you make a lot of radioactive stuff by this rapid neutron capture process. And this radioactive stuff is going to glow. Imagine kind of a bunch of nuclear bombs going off. That's a kilonova. So sorry, I gave away the trivia question. But this is the electromagnetic, so light signal that comes from the decay of radioactive isotopes that are produced and the merging of two neutron stars. Great. How would we know that this is actually making heavy elements? All right, so we have the idea. We know that, if you take neutrons, you can potentially make, heavier things. And I like to use this example of the forest with leaves. Okay, so we're trying to make heavy elements. If you remember back to your chemistry days, think of the valence shells, right? So these nuclei are eventually going to capture electrons and they're going to become atoms. Okay, these atoms have a lot of stuff around them. And that stuff makes it so that light has a harder time getting through a cloud of really dense and heavy stuff. So if you are producing, say, for example, the lanthanides, which I've highlighted, it's this row at the bottom, kind of, those are very atomically complex, right? So what that means is that they have a lot of electrons and they increase what's called the opacity. And what we would predict is that if you have a lot of these heavy lanthanides, they're going to increase the opacity of your ejecta. And what that's going to do is trap the photons, make them lose some energy, and turn them red. Okay, so they're going to be pushed towards a lower energy part of the electromagnetic spectrum. And you're going to see a red kilonova as compared to a blue kilonova, which would be lanthanide free. That's the prediction. Okay. Another thing that I should mention, neutron stars are really, really good at bending space-time. So if you've ever seen the example of like a marble on a trampoline compared to a bowling ball on a trampoline, neutron stars are kind of like the bowling ball. Okay, they're not the black holes that are going to, drop it off the face of the Earth, but neutron stars are really, really good at bending space-time. So when two merge together, they don't smash into each other. I was being a little dramatic, sorry about that. Really what ends up happening is that they kind of coalesce, right? And they spin into each other, kind of like a dance, or in this case, like two jet skis circling around each other. As they circle around each other, presumably faster and faster and faster, you're going to see this as ripples in space-time. Now, some of you might know, we have detectors for this now. So this is a really great era. We're in the era of multi-messenger astronomy. So not only can we see things with photons with our eyeballs, I always feel weird saying eyeballs, but yeah, we can see things with photons, we can see things in the electromagnetic spectrum, but we can also we can measure these changes in space-time itself that are coming from massive gravitationally significant objects spinning into each other, okay? We saw that. In 2017, we saw this, not from two black holes, not from a black hole and a neutron star, but from two neutron stars. Both a detector in Hanford. If you drive east like 3-4 hours, you'll go see a big L that are two tunnels perpendicular to each other. That is LIGO Hanford. We have one that is basically identical down in Livingston in Louisiana. And these measured that. And what they measured was the change in frequency, which you can see in the vertical axis as a function of time. And the fact that this is changing is going to to higher and higher frequencies. This is what's called the chirp. Okay, so this is the two neutron stars that are merging into each other faster and faster and faster until they just go pip, and then you get a black hole. It's great. It's wonderful. Okay, so we have measurements of this. We have seen this happen. We know that two neutron, we observed on August 17th of 2017. Of course, it happened a lot soon, earlier than that. But we measured the gravitational radiation from the merger of two neutron stars. That was super exciting. 2017 was a big year. We're still digging through interpreting this one observation that we've had. Yeah, here's the press release. LIGO and Virgo Virgo didn't really see. Okay, it doesn't matter. All right. Not only did we see it in gravitational waves, we also saw it in electromagnetic waves, the traditional way, the analog way of seeing it with our eyes. It played automatically. That's wonderful. That almost never happens. You can see the time evolution of basically this little tiny dot where the little yellow bars are. That's the kilonova. Okay, so a really useful comparison is down at the bottom. On the left, you can see what it looked like on August 17th. So see that little blue dot that says SSS17A. And then on the right, a couple days later, August 21st, you see the same dot. But look, now it's red. So great, we've made, presumably, lanthanides. That's wonderful. Again, this was a really, really big deal. We're all very excited about GW 2017-0817 and the accompanying electromagnetic observations. This is a slightly more technical view of it, just showing that you can see from the very rapidly decaying blue component all the way out to red. A lot of telescopes saw this. This was a big deal. All right, well, we're still missing the concrete identification of any specific isotopes. We say, well, we have this idea of if you make heavy elements, if you make lanthanides, you'll see this effect in the light curve, but that's not really an identification of any single nucleus, right? There was one exception to that. One measurement that people are claiming indicates the presence of strontium in the merger of two neutron stars. Hooray, okay. So, this would not be a science talk if I did not end it on, there's still so much that we don't know. And that's true, that's true. There's so many things that we still don't know. For example, I showed all of these nuclei. You have to capture, neutron capture all the way out, really, really far away from stability. We don't know the basic properties of those nuclei. That's a big question in nuclear astrophysics, okay? We don't know if neutron star mergers are actually good at making heavy elements. We know that they can. We don't know if they make enough to be the only ones who make it in the galaxy. We don't know if they make the solar abundance of our process material. We don't know. How do we actually identify specific elements? We have all this data, all this beautiful data, and I think there's been one claim of one element. So how do we know what specific elements are made? How do we identify this? And then, you know, these are extreme environments. You're taking two, you know, stellar corpses, throwing them at each other. Some of this material is moving at half the speed of light. It's very complicated. It's very messy. We're still trying to understand how that all evolves in time and what that looks like, and how the two tie together. So the evolution of the environment in which this happens and the nuclear physics that is involved in all of this together. And then finally, there's one other question, which is, could a neutron star merger ejecta pass as a fine Bordeaux? I don't know the answer to that question, but I would like to leave you just with the thought that there's this idea that we're made of stardust. Well, stardust, dead stardust. We're made of dead stardust. And so is our wine. So when you go shopping this year, just keep that in mind and let it, you know, kind of brighten your day. All right, with that, cheers. Thank you so much again. How was I on time? Oh, cool. Okay. I understand there's plenty of time for questions. So does anybody have any questions? Yeah.
Stars or, you know, multi-generational stars.
Yeah. One of the questions was, is there a distribution in the galactic disk, of different generations of stars? The answer to that is definitely yes. So there's a very interesting population of stars that doesn't have a lot of metals, right? So as these stars evolve, they make metals. More metal tends to mean a newer, younger star. There are some that have very small amounts of metal, but have a lot of R process, which means that they're very, very old, and they were enriched by 1 to 2 R process events very early in the history of the universe, of the galaxy. So yeah, there are definitely different generations, different enrichment events. We characterize this, or we quantify this all by metallicity for the different elements. So yes, definitely. Yeah.
Is that about how, like, we're able to observe that happening from when it splits?
This one?
Yeah,
oh, before this one. Ah, this one.
Yeah, like the delta, like it's the time we see for observation, or is it far longer than that? Or?
So it depends on which. Oh, so sorry. The question is whether this time scale is what we observe. The 30 seconds here, I think, is reasonable for the gravitational radiation, right? So 0 on this plot is when they merge. So it's the end of the coalescence event. Before that is when they're spiraling in on each other. that happens very quickly. When they're really far apart, we don't get a lot of gravitational radiation, and as they get closer together, that gravitational radiation gets intensified. And so, these things are incredibly sensitive. If you look into like, they compare it to, we can detect changes in space-time to like the width of an atom or something like tiny, tiny, tiny changes. It's very impressive. But, we're not going to see these things days and days ahead of time. But the electromagnetic radiation, now zero it's still coalescence time, but we see that after, right? So after all of this stuff has been ejected, that's when we see the radiation. And presumably we could see this for several days to years. Part of my job is figuring out what we can see for several days to years. But yeah, we have much longer time allowances on the electromagnetic side of things, but the gravitational radiation, it all happens very, very quickly. Yeah.
Come from these stellar events. They end up in red swarm. Are we able to detect? I mean, somehow they get from there to here. Are we able to detect in space the transit of these elements? Is there a factor in space that we can say there's a percentage of space that has these elements?
Yeah, that's a really interesting question, is whether we can detect basically how this how metallicity or enrichments, right, chemical enrichments from these types of events can be detected here on Earth, whether we can detect whether something happened recently. Maybe. So there are actually studies that are looking at this. One that's particularly interesting is, well, two that are particularly interesting. One is looking at the lunar regolith. Pardon my pronunciation if that's not right. But so the problem with Earth samples is that, well, we've tested atomic bombs. So we have a lot of radioactive stuff that if we're trying to tie this to stellar sources, it kind of messes up our readings. But there are two places that are relatively untouched from that, right? Because they evolve on their own geological timescales. One is going to be the moon. The moon, we didn't test bombs on the moon. The other is the seafloor. So one of the things, the seafloor, sorry. One of the things that they're measuring on the seafloor, and I think with the moon, is they're looking at the isotope ratio of plutonium. So plutonium is an R process element. It's one of those actinides that's up in the upper right corner that I showed you that you can only make through the R process, compared to iron 60, I believe. Iron 60 is made in supernovae. So what you can do is you can measure basically the ratio of those two isotopes and determine when a kilonova might have happened versus when a supernova might have happened. And people are definitely trying to do this, but again, it's very model dependent, and so we're trying to like get a better idea of, well, what do we understand and what do we need? But yes, definitely, people.
Measurement of space itself to say these elements are in transit, like there's space this minute but measurable amount of heavy.
Yeah,
in transit.
not really in space, but in stars. So for example, one of the earlier detections of a very R process enhanced star was in the Reticulum 2 dwarf galaxy. It's a dwarf spheroidal galaxy. So this is one of those galaxies that doesn't have a lot of stars. It's mostly dark matter, but for some reason it has some very R process heavy stars. So we know that something happened in that part of space that made those stars really R process rich and not the stars in the neighboring satellite dwarf spheroidal galaxy. So in that sense, in large scale, yeah, but not like isolated clouds of stuff. I think the closest to that I would imagine would be stellar streams, because I think those are like similar populations of stars. But I'm not an expert on that. So, but yeah. Okay. Yeah.
Are there any differences when it starts and the neutrino thing explodes and then creates another star and then there's the coalesce again and do it all over again?
So if there's a difference between when like neutron star like mergers happen and the next generation of stars, yeah. So so once two neutron stars merge, you get a black hole almost definitely. So that itself is not going to be very nucleosynthetically active because it's just curved space-time. There's no more real like matter as we think of it. So once you merge two neutron stars, they're basically useless. Maybe I shouldn't say that here. Black hole people don't hate me, please. But yeah, I mean, so when you have stars and they go supernova, and there is a very interesting question how you get two neutron stars together in the first place. But in terms of like neutron stars enriching other neutron stars, that doesn't really happen just because of the outcome of a neutron star merger. But yeah.
I've also heard like that black hole decay over time.
Ooh.
And if there are any sort of processes that or things that generate from this
Yeah, so the question is whether a black hole decaying over time could produce some kind of nucleosynthetic event, right? My instinct would be to say no, but just because I have a very elementary understanding of how black hole decay works, my understanding is that it happens because of pair annihilation. So you create electron-positron pairs near the event horizon of the black hole. It's very energetic, but you're not creating nucleons really, right? So you need neutrons and protons, and for something like an R process, you need those neutrons. So I think black hole decay happens over very, very like cosmological timescales, and is not really producing the nucleons that we need to do nucleosynthesis. But what you can do is you can throw a black hole at a neutron star. And in doing so, I love smashing things together. It's great. It's super fun. If only I could do it in real life. Yeah, if you were to take a black hole and a neutron star and have them merge, that black hole is going to rip that neutron star apart, and in doing so, it's going to eject material much in the same way that two neutron stars would. So you would have a different nucleosynthetic process. Presumably, that's what we're trying to figure out is how different it would look. But you would have a kilonova type event. Presumably, we're still trying to figure that out. Yeah, but yeah, definitely. If you throw a black hole at a neutron star, but just a black hole by itself, no, as far as I know. Okay, thank you for all the questions and for being here.
All right, let's thank Kelsey again for that great talk. We will now take a brief intermission, so you can feel free to restock on beer, patronize this wonderful establishment, and we'll come back with trivia answers in our second time. you for helping to patronize this establishment and help us keep doing Astro on Tap at various events. We are now going to go into the answers to the trivia questions. And there may be some spoilers for the next talk, so keep an eye out for that. So, question number 1. When two neutron stars collide, the bright explosion that follows is called, as you found out, a kilonova. Thank you, Kelsey. Question 2. Neutron star mergers are major cosmic factories for which kind of material? The answer is B, heavy elements. Gold is an example of one, although radioactive elements are perhaps more interesting. Question 3. The R process was describes how the universe creates heavy atomic nuclei. Very exciting, and it does it rapidly as opposed to the slow S process. Question 4. Which particles involved in neutron star mergers can change their flavor? This is neutrinos. There are many different kinds of neutrinos, and they're all very strange. Sorry, weird. Strange is a buzzword. Sorry, can't say that. 5. Kilonova observations help scientists learn about how dense nuclear matter behaves. There's a lot of fun stuff going on in there. Question number 6. Ultra-faint dwarf galaxies discovered by the Dark Energy Survey are important because they are very rich in dark matter. The Dark Energy Survey just found some dark matter. It's crazy. Question 7. Gaia's main mission is to measure B, the positions and motions of the stars. This is also sometimes called kinematics, because we are measuring motion. It's great at what it does. Question 8. The motion of satellite galaxies around the Milky Way is especially useful for studying dark matter because, believe it or not, the question that has dark matter in it is correct, because dark matter dominates their gravity. Question 9. The Eureka simulations model how Milky Way-like galaxies grow. This is true. And question 10. The Apostle simulations were created to study the environment of the local group, which includes the Milky Way and Andromeda. These are some somewhat straightforward questions this time. The difficulty varies wildly from month to month. So, one team got 10 out of 10, and it was indeed the professional astronomers, so good job. Luckily for the rest of you, they don't get prizes. I'm just saying it because I would. I think I'd have to revoke some PhDs if they didn't get them all right. But there are 2 teams that got 9 correct.
Whoa!
Now, one team, you know, one of the teams that got 9 points is the team Kelsey's friends. They claim that Kelsey did not tell them anything. So they're engineers, so they didn't know anything about this beforehand. And the other winning team does not have a team name listed, but drew some pretty stars and galaxies at the bottom of Is that also you? All right. Well, here, let me. We are Kelsey's friends. Oh, sorry. So, with that being the case, there are also several teams that got 8 correct, and there are actually a lot of them. So, one of the teams that got 8 correct is this team is always up here, and I always pronounce it wrong. Halians. Yeah, nice. Team Peely Wop. I think people just like making me say strange things. Team, I think DLB is the team name, potentially. Maybe. Good job. We have Team Foolish Mortals. Team Titan Uranus. Good job. And those are our 8-point teams. So if you got 8 or 9 points and you would like to collect a prize, we have some nice trivia prizes. We're going to transition pretty quickly to the next talk, but if you want to come up to us after the talk to get your prize, you can. Or you could also come up right now. Don't do that. If you want to come up after the talk, you can come get your prize. And I have to switch the slideshow, but then I'll introduce the next speaker. Give me 1 minute. You could have.
Hi, it's me. I'm the problem.
All right. Here is your
Hold this,
clicker,
click this.
and I will introduce you, and then I'll hand you this. Thank you. All right. So our last speaker was Kelsey Lund, and our next speaker is Alex Riley from Lund University. Fun coincidence. He's been in all sorts of places all over Europe and the US, and is currently at Lund University, which is in Sweden, so I'm told. He works on dark matter and streams, and is currently in town for the dark matter conference/workshop that's going on at UW. But he won't necessarily be talking about streams. Instead, we'll be telling you about the next 10 years of astronomy, which is very exciting. So let's give a big welcoming round of applause.
Okay, I'm situated. I've got the mic, I've got the clicker, and I've got the drink over here. So we're all good. Okay. So yes, hi everyone. My name is Alex Riley, and I am gonna talk about sort of the next 10 years of astronomy, and more specifically how like we as astronomers have planned out the next 10 years of astronomy. Now, it's worth noting that this talk, I did this at an AOT all the way back in 2021, and then there's going to be kind of an update sort of towards the end, like we're sort of five-ish years out of that. So bear that in mind a little bit. So what do astronomers want to know? We just heard an excellent talk about sort of how the chemistry of the universe evolves over time, and how we can study nucleosynthesis and all these things. There's a lot of, there's more than this, but like broadly, like you have these like big things like how do galaxies form? What is the nature of dark matter, dark energy, how things form in the universe? What governs all of that? And then there's like all the exoplanet people love to talk about, like, are we alone? Or this kind of thing, right? So like these are kind of the three like really big buckets. If we're gonna like draw three big buckets, these are as good as we can do. But there's like kind of like a broader question that's like, how do we decide between these, how we go about studying these things, right? All of these different science cases, they all really want to build really big telescopes, right? But like the specifics of those will change depending on if an exoplanet person's building the big telescope or the galaxy formation person's building the really big telescope. So how do we decide between these? Yeah, okay, great. And the answer to that is this thing called the decadal survey, decadal being once every 10 years, okay? So the most recent one of these was called Astro 2020, a decadal survey on astronomy and astrophysics. Again, we're great at naming things here. And we're gonna kind of walk through this idea, like we're gonna walk through a little bit how we sort of came up, what was the process that we decided to make this decadal survey, and then a little bit like, okay, what did we actually recommend in all these? What are the things that astronomers are going to build in the next 10 years or so? So the scope of this was like massive. Like think like one of the biggest, like this is the astronomy group project every 10 years, right? So, you know, there's something like call it like, I think the AAS says there's like 5,000 professional astronomers. You have to, that's like professor level and above sort of is how they sort of draw that line. So, but there's like a lot of us, and everyone wants their science to be like important, central to all this. And you kind of need to like navigate all that. So the way this was handled, so every 10 years you do the survey and you pick one or two like chairs, people who need to like steer all this process. In 2020, this was Fiona Harrison, who's at Caltech on the left, and then Rob Kennicott, who is at A&M, which is where I did my PhD. That's why there's a logo next to him. And the way that this worked is if like you would sort of get your friends together and write what's called a white paper, right? So this is like maybe 10-ish pages of you making your pitch for whatever science you like, or like things that are adjacent to science. So there were 860 of those white papers submitted, of which 573 were science, and then the other like 300 or so were, let's call them like how we should be doing astronomy. Things like worrying about we should be funding more theory, or we should be I'm trying to think think things like EDI or how we should teach or all this other stuff. There were 614 pages in the final report, so you compress the 860 white papers, you kind of tier rank everything, and then make a final report that's 600 pages. There were 13 panels that did this. So think like there was a panel that was very focused on all the gravitational wave stuff, and there was another panel that was focused on galaxy evolution, right? And so the galaxy evolution panel would read all the galaxy evolution white papers and then come up with their recommendations, and then you had one sort of steering committee over the whole thing. The org chart for this is ridiculous. We're not going to show it. So why is the decadal effective? Like why go through this process like at all? And there's kind of three main reasons. So one is obviously this is like a really community-driven process, right? We don't want like one person getting together in a room with their best friends and deciding where astronomy is going to go. And this is actually a little bit how it was done in the 30s, and people didn't like that. And so we came up with something better. It's perceived as neutral, and what I mean by that is that like the people who are the heads of like funding agencies and Congress think that this is neutral, right? Which is actually like really important. Yeah. Okay. And so as a result, it's viewed as like legit, right? Like we went through this really big communal process. We came as a decision like together through all this like steering committees and stuff. And that helps you when you are going through successive different administrations from different parties, right? Because we're planning for 10 years. The American political system doesn't operate on 10 years, right? So you need something that withstands all that sort of thing. And then the third one is that these reports are actually mandated by Congress, and that's actually kind of rare. So the National Academy, they'll like put together a whole bunch of like reports and consensus documents and all these other things. But the list of things that's mandated by Congress is actually pretty small, and Congress cares because they care more because if you tell people, hey, go figure this out and then come back, that's more important to them. So this is like a line item in a lot of like NSF and NASA budgets is like handling the decadal process. So these three things sort of together give like a stamp of legitimacy to whatever the decadal says. And that's sort of like the shroud of importance that we sort of put onto this thing. So you're probably familiar with like a lot of the big ticket items that came out of previous decadals. So things like the Hubble Space Telescope, the VLA where contact happened, the Chandra X-ray Observatory, JDub in 2000, and then Roman and Rubin, which there's a lot of involvement at UW here for Rubin in particular. All of these were like the big ticket items of their respective decadals. Okay, and so of the sort of menu of big ticket telescope items that the Astro 2020 decadal process was considering, there were essentially four that sort of emerged. Going from left to right, we have LINX, which is like an X-ray thing, HabEx, which looks at specifically exoplanets, like habitable exoplanet was the idea. LUVOIR, which is large ultraviolet optical infrared telescope. Okay, that's important. Remember that order. It's important. We're going to come back to it. Okay, and then Origins, which honestly I don't remember. Okay, if there are any Origins people, I'm sorry, but like you missed the I don't know. It was a very crowded field. Okay, and Origins, this guy was fourth. All right, so who is this for? I've kind of alluded to this already. There's kind of two like groups that it's really important for. So there's the funding agencies directly. So these are the people who actually, Congress allocates some amount of money to them, and then they distribute it to all of the astronomers, et cetera, all the telescope surveys, all these sorts of things. So the funding agencies care a lot, and this is sort of The big three are NSF, the National Science Foundation, NASA, we all know and love. We have their patches on our sleeves and all these things. And then the Department of Energy, DOE, sort of cares a little bit because you start getting into like, they sort of think they can harness dark energy to be like the next weapon or whatever. Biggest con we ever pulled, name your thing dark energy, and the DOE cares suddenly. So they care a little bit. Like the big players here are NASA and NSF respectively. NASA being space-based, NSF being ground-based. That's kind of how that breaks down. And then the other big party here is Congress and everyone that, like, whenever Congress allocates funding, there's also like the Office of Management and Budget and all those other things that sort of interface with that. So like there's like these like big government agencies and then also the people who actually like write the checks at the end of the day. And it's also like, the decadal is also like a key document for when astronomers go and advocate for themselves every year. So this will sort of happen, this was ages ago. This was probably like 2018 or something like that. Like, you know, every year the American Astronomical Society sends like 20 or so astronomers to go advocate for swing states, basically, to like really like put pressure on these things. One of these people was my good friend Darnie, who I actually talked to this morning about like some of these talks for like how this is going now. And so we'll get to that in the end. Anyway, Darnie's in DC now, doing a lot of like funding advocacy work and whatnot. Okay, so I've talked a lot about like the process overall. All right, Alex, what's actually in the Astro 2020, the actual decadal survey? So there were three, the formatting here might get interesting. Okay, there were basically like three major goals that the decadal survey highlighted. This is sort of a reshuffle. This is kind of a reshuffle of the things I had at the very beginning of my slide. That was on purpose. So pathways to habitable worlds. We want to find all the exoplanets that are in the habitable zone, right? Like, and sort of study all those and, you know, find life or whatever. There's the what they called new windows in the dynamic universe. This is like taking pictures of black holes and all these like really exciting things. And then what they called unveiling the drivers of galaxy growth. This is like everything else, basically. It's fine. Did we skip a slide? No, we're good. Okay. So we remember our cast of 4 characters, our possible whatever like bachelorettes or things like this. So the decadal survey kind of looked at this menu of like 4 like really ambitious projects basically, and was like, what if we just like take 2 and shove them together? And so the like next flagship mission, and remember like LUVOIR, large ultraviolet optical infrared telescope. Okay, yeah. All right, so the next flagship mission, this is like almost straight from the decadal, is an Ultra Hubble, an all-purpose infrared optical ultraviolet observatory with a 6-meter mirror. Okay, so this is again like Ultra Hubble kind of says all you need, and then the wavelengths there, that's like a very large range of wavelengths, all the way like into the ultraviolet, which is kind of the extreme of what Hubble can handle, all the way into the infrared, like pretty broad range of stuff going on here. This mirror, once it, like, you know, if it were to launch, would have something like, I don't know where these numbers came from. This is just like from like the decadal. This is like 250% like resolution. So how like spatially the things that you can see versus the stuff that's too fuzzy and you can't see. And 6 times the light gathering power of Hubble, right? So this is all very ambitious, very exciting. It would be ready by 2040. Remember, decadal, 10. Ready by 2040 cost $11 billion. For context, JDub was like 7-ish. So we're already, this is like the initial pitch is $11 billion. Yeah, table stakes. So there were memes about all this. This is when Twitter, like Astro Twitter, was like really fun. And so I'll read this. The most jarring part of Astro 2020 for me personally is realizing that according to this chart, we'll see the chart in a second, I'll be in my 50s when Mini LouvWire launches. People were already calling this thing Mini LouvWire. And then I got in on the action. It's only a LouvWire if it's from the Loire Valley in France. Otherwise, it's just a sparkling large infrared optical ultraviolet space telescope. It's not my best tweet, but it's like way up there. Okay. All right. Okay. So basically like this space telescope was like the key mission, key driver, like big ticket item from the decadal survey. Skipping the memes. One thing that the decadal sort of realized was, oh, we come up with an idea for what the decadal like big ticket item should be, but then that thing usually launches somewhere between 15 and 18 years from whenever we publish our report. This was true for Roman. This was true for JW. All the way. And often those things were greenlit with unproven tech. Like the detectors that JW has didn't exist when they said, we're going to build JW this way, and it's going to have these detectors, okay? And that is part of why JW, amongst others, was very expensive, over budget, delayed, et cetera, et cetera. And so they came up with this idea that was basically, we're going to, delays, cost overruns. Starting now, we're going to figure out if we can actually build the detector or build what we're going to say before we start building the actual telescope. I know, huge. Again, astronomy in the 30s was wild, okay? Anywho, so they had this the title slide here is the Mission and Technology Maturation Program. And the idea was, okay, we're going to like for the instrument that's going to get launched in 2040, in like 2021 to 2029, we should be proving the tech, like building, like if the tech doesn't exist, we're going to prove it, sort of do all this development early so that you don't get these like massive cost overruns and gaps, et cetera. Whenever you talk to an engineer about this, they're like, well, yeah, duh. Again, astronomers, okay? Right. So okay. So these were like the really big space missions, the ones that are all the elementary schools, they like know these names like Hubble and Roman and etc. There were other things that were in the decadal. We're gonna go through some of them now. They had one of these things was now we're going back onto the ground. We're going from NASA to where the NSF funds all their telescopes. And the idea was to build essentially the biggest telescopes ever, okay? Biggest in mirror size. So when we name these things, the extremely large telescopes, so there were kind of like two, very similar to how there were like four space missions, there were two ground-based ideas that are going on, either the giant Magellan telescope or the 30-meter telescope, okay? So like for context here, the current world-class mirrors, are, again, drunk, are either like they're around like 8 to 12 meters in diameter. These, like the GMT, TMT, these like ELTs, are 30 to 40 meters in size. So like massive, huge, like technological feats, science capabilities, all of it. The decadal was this was a very politically hot fight going on between these two missions. The decadal basically didn't want to take sides here and said, okay, NSF has enough money with all of our other recommended stuff, has enough money to fund either 25% of both or 50% of one telescope, and sort of said, astronomers, figure it out yourselves. And that's to the tune, so that dollar amount would be like 1.6 billion. That's not 1.6 billion in like the fiscal year 2025. That's like spread over like maybe like a decade or so, okay? And then it's worth noting that like Europe is already kind of ahead of the game. They have their extremely large, like European extremely large telescope. Yeah. And this like building one of these would basically catch up to where Europe is like planning to go, but with like considerable hurdles to go, like huge politics, literally. Well, it's like skipping thing. Okay. There were a couple of other like big next generation recommendations. One of these was CMBS4, so looking at like the imprint of the cosmic microwave background, the very earliest bit like baby picture of the universe, and learning a whole bunch of things like inflation, all this stuff. There was the next generation VLA, which has the resolution to see planet formation in action, like doing time series of like an individual planet in a protoplanetary disk forming. Was sort of the basic driving idea there. There's IceCube Gen 2, which is high energy neutrinos from extreme events, whatever that means. And then we heard about LIGO in the last talk. There was also ideas for upgrading the detectors on LIGO and doing tech development for LIGO, the LIGO successor, which is, I kid you not, LIGO in space. Okay, that's all you need to know. So all these things were kind of like the amount of time I'm spending on this is about the amount of time the decadal spent on this too, right? They're just kind of chucking everything in, right? And then they kind of had this like crazy figure that this was kind of how they viewed all these things. So like they're like individual bits of this. It was sort of like not a pyramid scheme, but you know, something. So like at the bottom here was like, you know, advancing theory, doing laboratory measurements, diversifying the science workforce, balancing the portfolio, whatever that means. And then all the way up to at the very top was like their three big missions, and then also this like you know, mini LUVOIR space telescope kind of thing. So if you're thinking that's a lot of stuff, that's what everyone else thought. My quick read of the Astro 2020 is basically, let's do it, it's all great. This was the vibe at the time. And if you're thinking, geez, Alex, all that sounds pretty expensive, you're right. But actually not. So we'll get there. We'll get there. People reading ahead. Right, so like links and origins were around like 10 billion, and LUVOIR A, which was like, so LUVOIR was such an ambitious mission that they had LUVOIR A, and then LUVOIR B, which was scaled down version of everything, right? So LUVOIR A, like the big ambitious thing was like $15 billion, which is like not drastically far away from the amount of $100 bills that the US military lost, LOL, oops, in Afghanistan in 2012. Right? Like, come on. So like you need, again, there are these really big numbers, but you kind of need to put them in context of like the other things that the US government thinks about sometimes. And then this graph keeps going. So at the very bottom there is the annual Pentagon budget. And yeah, so other things here. So like all of these like costs, they sound really big to us, but they dwarf what the government sort of generally cares about, right? It's a very like small amount of money, but you need to get the attention of people who are writing really big checks, right? So that's kind of the idea. Okay, so when I gave this talk in 2021, this was the end. We took questions and like moved on with the evening. Now we're doing, okay, so that was all the way back in 2021. We're like, you know, getting into the end of 2025. Sorry, everyone. And we're like sort of 5 years in, which is crazy for all the people who were around when the last decadal was happening. Like I shriveled when I realized this. So we're gonna cover like, okay, what's going on since then, and I was originally gonna do like you know, sort of more recent years, and then specifically like since, you know, January of 2025 for reasons. But we're just gonna do bad and good like that, because there's more good here than I actually like thought there was going into my chat with the people who do science policy, right? So we're gonna go through the bad really quick, and I'm not saying there's not a lot of bad, but there is some bad. So one of these big ones is that some of these highly recommended missions, like super ambitious, would change our understanding of the universe, are just getting shut down. So the big one here, the one that kind of woke up all the astronomers to like, oh, this might be different, was CMBS4, which was, if we go all the way back, that was like the first one of like the, other major recommendations, right? So CMBS4, this like cosmic microwave background explorer, was, super ambitious idea. It was well supported by both the astronomers and the particle physicists, which is really hard. And it was like recommended by several decadals on both sides of that aisle, right? So when this got canceled, everyone got quiet for a bit. They were like, oh, like we're gonna need to, all these other things that haven't gotten canceled, we're actually gonna need to kind of fight for them. And so that was like a big clarifying moment. The newspaper of record that uses this font. So the other idea here is that there are whole categories of science that are getting turned off, right? So for whatever reason, anything the NSF has to do with Antarctica is suddenly getting shut down for like reasons I don't quite understand, but like this is like a particularly like sort of noteworthy thing. Here we're talking about like the South Pole Telescope and those other things like IceCube Gen 2 is sort of on the chopping block maybe here. And then the other one, which is kind of, in my opinion, like the most bad, and this was the one that sort of brought up a lot of time when I was talking with science policy experts, was when you get rid of a whole bunch of people who have been in the NSF for a while, that kind of expertise is just sort of disintegrates, right? There's a, so like, normally well, still now, there's a group of astronomers who, in between decadals, still meets with like the really big funding agencies every 6 months or so, and says, okay, so you have all these plans, you have all this stuff. How does this advance the goals of the previous decadal? They're meant to like really drive home that point. When you're doing that process with people who have been in the job for 10, 15, 20 years, you build relationships, and it's a lot easier to sort of, get things moving, navigate the massive bureaucracy that is the U.S. government, all these things. And that expertise kind of has crumbled a little bit. All these people who have been on these committees, who have been meeting with funding agencies every 6 months or so, now they're meeting with brand new people. And that's like making things harder for them. So this was like kind of the biggest, like, when I was talking with the science policy people, this was like the big thing, that like this was what they were actually worried about. Like, yes, CMBS4 got canceled. That's really bad. We should try to fight for it and all these things. But like this was the big thing that's going to make everything else harder to sort of advocate for. Okay, I swear that's the end of the bad. Okay, now the good, the really important thing. So we went from the beginning of the talk, right? Beginning of my slides. I had, these were the strengths of the decadal survey, right? This, big, massive group project that is perceived as being a big, massive group project. Like this is the consensus amongst the astronomy community, and it's sort of mandated by Congress. All of these things that were the decadal strengths are still true. And that was actually like, I was surprised by that, but again, science policy people, they were saying, like, yeah, it's still useful to go into, the smoke-filled rooms and say, the decadal says this. We should be supporting the astronomers as best as we can, right? And I was expecting that to be like, I was going into these conversations, I was like, okay, everyone's like ignoring the decadal now, but that's not actually like the case. All of these strengths are still there. And one useful example, one useful illustration of all of this is actually the history of Roman. So this is the space mission that's going to get launched in mid-2027, pray to whatever you want. So in sort of fiscal years 2019 and 2020, the administration at the time set Roman funding to zero, essentially tried to cancel Roman in their sort of budget request, right? So there's this meme in like science policy circles that the the presidential administration, actually regardless of which party, sends over their budget request, and then Congress like takes that in their hands, crumples it up, chucks it in the trash, and writes whatever they want to do anyways. Yes? So, and that's actually what Congress did. Like they said, well, no, the astronomy community said Roman is super important to us. And both times set funding to basically normal levels, like basically ignored the whole thing. Said Roman is super important. We've invested so much time into this. It's like it was the recommendation in the 2010 decadal. We're gonna do it, basically. Fiscal year. This should say 2026. Sorry. Fiscal year 2026. Same thing happened in the very recent, like call it like April, I think. New administration set the Roman funding to twiddle zero. And there's already similar pushback from the science committees in the respective House and Senate, right? Like it's the same, like this is like a really weird bit where the normal rules are still sort of applying. And that sort of gave me hope that like maybe this decadal process is all still happening. There is still a point to doing the decadal, and we just need to fight for what it says now. So yeah, thank you. Questions? Oh. Okay, which decadal suggestion is going to give us the best pictures? When the large infrared optical ultraviolet telescope launches, that's probably going to give us the best pictures. I love I built my like in the beginning of my, well, still now, a lot of my scientific career has been from ground-based imaging, but like the space-based people, they know what they're doing. Like you get way better images from space. So yeah, so that probably. Okay, let's go over there.
Is there any of those projects that you would scrap to bring back the penny?
I like where your mind is at. I wouldn't bring back the penny, and so I reject the premise. But wait. So a project I'd bring back, like something that got canceled or scrap? Oh, scrap. My answer normally would be CMBS4. Like, sorry, if there's any CMB people in the crowd who want to defend themselves, go for it. But like, yeah. Wait, you say there are no CMB people? Oh, okay. So yeah, I don't know. NGVLA, the planet people have a lot of money. There. Okay, done. Yeah. All right. Any other questions that'll put me in hot water? Yes.
So if you were to design a process kind of from the ground up to direct the astronomy community and their funding, how closely do you think that process would mirror what we have now?
That's a really good question. So if I were to build something from the ground up, how close would it be to what we have now? Honestly, very close. So the problem here is that group projects are hard, right? Everyone that, yeah. There are some. So like when people are like, oh man, the decadal's an imperfect process. A lot of those critiques come down to how the committees are formed. So we're all the way back at the beginning, we were like, there's like 20 committees or so and one steering committee. Those are kind of the chairs just sort of pick those people, including like what committees get formed. And so that step is probably, I don't know how you make that democratic, but that's kind of where I would go there. That's kind of the weakest link in this whole thing, honestly. But that's like very, that's not a huge change. And that sort of shows like how like, again, the decadal's been an iterative process. I'm sure 1970 people had lots of complaints about it. We got better. since 1970. So yeah, so but that kind of like chair committee selection, I think, is the big thing. Okay, sitting at the table, and then we'll walk this way.
Are they starting to put together committees now for the after 2030?
Yes, I almost drank the mic. I don't know if anyone saw that. So the way that this typically worked is, so I want to say that like sort of around like 2018 is when the previous decadal chairs were selected. You had like again smoke-filled rooms figuring out who all the chairs would be, and then this kind of this writing period of actually submitting white papers was basically all this got like crunched up with COVID, so there's like weird stuff going on there. But that was largely like, call it 2019 bleeding in through 2020 and into 2021. Whoops, sorry. So yeah, that's about how long it takes. So like when I'm saying like astronomers strap in 2028, like 3 years, we're gonna be doing Astro 2030. Yeah, that's coming up soon. But yeah, something like that. Yeah. Right there. I'm honored because I've been in Europe for 4 years. Yeah. So the decadal process, voice crack. The decadal process was honestly copied by sort of how they do things in Europe. Like the Europeans sort of just have this built in their DNA. It's like this very communal process with all the committees and whatnot. And that just sort of happens on like a sort of continuous basis, basically. For the other countries you mentioned, I'm not really sure. Australia, I don't actually have any clue. That's an interesting blind spot in my brain. But yeah, so generally, astronomers are incredibly collaborative. I'm in collaborations with like many people scattered across the globe. Telecons are a pain to schedule and all that kind of thing. But kind of the decadal processes are advocating to governments. And so as a result, that's when you get a lot of like, oh, we need to build the best telescopes because otherwise China's going to beat us or whatever. So yeah, that's why that kind of bleeds in, and that's why this was an American-centric view. But like other countries do some things that are like this. But it's all communicated up to like their governments to ask for funding, basically. Yes.
Right, and I'm sure this happens every time. But something that struck me was that almost like 40% of papers mentioned, like papers that had to do with our approaching astronomy. What would you say have been some of the most significant changes over the years from these papers? Or like even how we're doing it?
Very good question. So some of this is like things that the astronomy community is already pretty amenable to. So like, give more money to theorists so we can understand what's going on, or that kind of thing, right? Basic ideas. The one, and I'll say this, we're recording, it's fine. The one where I was actually kind of shocked at how far the decadal came out was essentially viewing treating your fellow scientists like crap. That was, the recommendation was we should be treating things like sexual harassment, all these other like nasty topics, like we do, faking your science results. Like there should be a similar level of radar going off, ostracizing them from the community, these kinds of things. I wasn't expecting that, and yeah, sure. I can't say that's been implemented, but it was kind of huge that the decadal said that, and yeah, that was like a big positive surprise to me. Yeah. I think you've had your hand up for a while. Yeah.
Climate change, there's a certain segment that discounts the premise of it. In the work you're doing, is there a similar kind of discrediting of ideas, scientific ideas that were proposed for research.
You mean like how we do science, or like a particular like field of study that rejects a lot of astronomy convention?
Particular field of the assumptions of the science you're doing.
Have you heard about MOND? I won't leave it. I won't leave it here. There are lots of people who think that dark matter is fake and that it's all normal gravity. Okay, sorry. No. Right, a lot, way more people than there should be. Not a high fraction. Not a high fraction of astronomers. We're gonna save it. There was another hand. Yeah.
So you talked about how this is basically like a U.S.-centric process, and then the other countries have their. Is there any provisions for like managing international cooperation with these?
Yeah. So not at the decadal level. Usually at best it's like, oh, we should fund this thing that also the Europeans have promised to chuck in a whole bunch of money for. At the astronomer level, that happens quite a lot. You have these big collaborations that sort of go in for time and all this stuff. I'm trying to think of like good examples now. Gravitational waves is a good one. There's a survey called Euclid that is mostly Europeans, but like a lot of Canadians and some Americans are involved. But those are usually at the astronomer level, not really at the government level. So yeah. Cool. I'm getting the thumbs up, so I think I'm cut off. You want your mic, or?
No, that's your mic.
Okay.
All right. Well, let's thank our. Thank you all so much for coming. There will, as far as I'm aware, not be an Astronomy on Tap talk in December, because all the people who would give talks are not going to be here. They're like going home and stuff. But we'll be starting up again in January, and I'm still hunting around if you have any suggestions for venues, because I'm still hunting around for different places. So send me an email, and I just said that, but you don't actually know what my email is. But if you want to, if you have any suggestions, please come talk to me. And I will see you all in January. Thank you so much. Have a nice night.